Well, hello and welcome again to our journey into number theory, and we've been having a look at the L functions defined on the Dirichlet characters, and we did a little warm-up last time to Dirichlet's theorem. So before we continue on with that, I wanted to say a little bit about Dirichlet density, and I'm going to give you a rather strange looking definition of what we mean by that. So we take a set of positive primes P. Generally this will be an infinite set, and it's said to have Dirichlet density dp if this limit, which we're going to call dp if it exists, so this is the limit as s goes to 1 from above. We take a sum over all the primes in this particular set P, and we take 1 over p to the s, divided by the log of 1 over s minus 1. So if that limit exists, then we're going to call that the Dirichlet density of the set P. It's a rather strange definition. It's motivated by the fact that if you take the log of the zeta function and divide it by log of 1 on s minus 1, and you work out that limit, that one turns out to be 1. So we'll come back to that a bit later, but you might like to do a little exercise to convince yourself that that is actually true. You need to use L'Hopital's rule, I think, to get that thing out. So that tells me that the set of all primes then has Dirichlet density 1, as we might expect. If P is any finite set of primes, then of course this will be just a finite number up here, and this is going to infinity, so this will just give you d of p as 0. And on the other hand, if P contains all but a finite number of primes, then dp is 1. The more natural definition of density might be to take the number of primes in P less than some number n and divide this by pi of n, the number of primes in total up to n, then take a limit as n goes to infinity. This natural density, when it exists, can be shown to be the same as the Dirichlet density. But there are sets for which do not have a natural density, but which do have a Dirichlet density. Without going into detail, I just mention an example here. The set of all primes whose first digit is 1 has a Dirichlet density, interestingly, log of 2 to the base 10, which is about 0.69, so about 0.7. So that means about about 7/10 of the time a prime will have its first digit 1. More generally, if the first digit is k, then it can be shown the Dirichlet density is log to the base 10 of k plus 1 over k. Dirichlet proved, and we will as well, that if you take two numbers that are relatively prime, GCD is 1, and you take the set of primes that are congruent to B mod A, that's the set of primes in this arithmetic progression, then the Dirichlet density of P turns out to be 1 over 5a, where phi is Euler's phi function. And we will actually prove that a bit later on. Just as an example, if we look at the example we did above, where we're looking at the primes congruent to 1 mod 4, so if we take P as the set of primes 1 mod 4, then we'll see that the Dirichlet density is, as you might expect, a half. You might naively and correctly feel that half the primes are 1 mod 4 primes and half the primes are minus 1 mod 4 primes, and that we will see is indeed the case. There is some odd behaviour, I might say, about the number of primes up to some point, 1 mod 4 and minus 1 mod 4. In any finite list of these, some strange things happen, but in the limit, the Dirichlet density of each is a half. So to verify this is correct, we're going to just use the results in the previous section. So I take chi1 and chi2 as in the above example. So remember, L of s and chi1 was just this sum. And I'm going to write this sum, I'm going to add in all the extra terms to turn it into the zeta function, and then I better subtract them again. And by the way, I can do whatever I like with this series, because for s bigger than 1, this is absolutely convergent. and so I can rearrange the terms. There's no issue with that, provided s is, in all of this stuff I'm assuming s is bigger than 1. And this one here, we're tempted to factor out a common factor of 1 over 2 to the s, which I do, and then to our great surprise, back comes the zeta function again. So I can write this as 1 minus 1 over 2 to the s times zeta of s. So taking logs of both sides, then the log of this is going to be the log of 1 minus 1 on 2 to the s plus the log of zeta of s. Now, we also saw above that when you take the sum of the logs of these two, then you just get twice the sum of 1 on p to the s, where these p's are the 1 mod 4 primes, and we had a remainder term which was bounded as s went to 1. So plugging all this back into our formula for the Dirichlet density, we now have to look at the limit. So I've got to take this quantity up here and divide that by the log of 1 on 1 minus s. So this sum here we can write as 1/2 of this plus this, and then minus the R3. So I take the half out the front, and I end up with that sum there. Now we have an expression for this one, L of the log of L of s and chi1. We had an expression up here for that. There it is here. So I just plug that into here, so I get that plus that. We've still got this sum here. We've still got R3, and this is divided by this logarithm. Now we now think of what's happening as s goes to 1 from above. Well, this term here is just approaching log of 1/2 as s goes to 1, which is certainly bounded. It's a finite number. This one we know is also bounded, so this is some finite number. This is bounded. So each of these terms, the limit of each of these terms over this will be 0. And all we're left with is the log of zeta of s on the log of 1 on 1 minus s. And we mentioned before that that goes to 1. So this limit in here is just going to 1, and we're left with a half out the front. That's a little example of Dirichlet density, and we'll come back to it a bit later when we look at getting this result that I mentioned before of the Dirichlet density of the primes in this particular arithmetic progression. I wanted to do yet another example because just to cement in the ideas that we're doing before we actually start looking at the proof and the technical details. And so we're going to look at the primes now modulo 8. So the character table for U8 is this. We've seen this one before. And we're going to define the Dirichlet character modulo 8. Well, if our n is 0, then the value of the Dirichlet character is 0. I've gone back to putting the little superscript naught here for a second. And then if it's an odd number, so it'll be congruent to one of these four numbers here, modulo 8, and that will simply be chi I of n hat, where you take n and you read it mod 8 and you get n hat. Now, as before, I'm going to drop the superscript 0 and just look at this Dirichlet character here. Now, since the characters are real, we'll take s to be real, and we'll, as usual, take s bigger than 1. As before, we're going to define the L functions for each of these chi's. So there it is. And as before, we saw that the log of L of s and chi I is just the sum over p and on prime of chi I of p on p to the s, plus you're going to get some remainder. And this will be true for I equals 1, 2, 3, and 4. And each of these remainders is bounded as s goes to 1 from above. The proofs of these are all exactly the same as we saw in the earlier section. Now, what we want to do is we want to pick out the primes that are 1 mod 8, the primes that are 3 mod 8, 5 mod 8, and 7 mod 8. And to do that, we simply observe that, firstly, if I add the characters together, looking down the rows, if we come back to here for the moment, if I look at adding the characters, then along here, if I add these four numbers, I get 4. If I add those, I get 0. Add those, you get 0. Add those, you get 0. So the sum of the characters evaluated at n will be 0 if n is not 1 mod 8, but it will be 4 if n is 1 mod 8. Well, similarly, I'll leave you to refer back to the table. If you do chi1 minus chi2 plus chi3 minus chi4, then all of the numbers are 0, except when you've got the second column where n is 3 mod 8, and then you get 4 again. Similarly, this sum produces 4 for n is 5 mod 8, and this one produces 4 for 7 mod 8. The choice of signs here is of course going to be connected with the orthogonality properties that we saw before. And so we'll need to use the orthogonality properties a bit later on when we're trying to decide what signs and things we use here. So if I add together then the logs of the L functions, that I get, as we saw before, I get 4 times p congruent to 1 mod 8, 1 on p to the s, plus some remainder term, and that remainder is bounded as s goes to 1, because it's just simply the sum. This a is going to be r1 plus r2 plus r3 plus r4. Each one of those is bounded. Similarly, if I use the second line up here and I take the log of that minus the log of that plus the log minus the log, that picks out the 3 mod 8 primes, plus again the sum term which is bounded because s goes to 1 from above. Now again, if we now look at this line, what this says here, if we can show that each of these 3 L functions is bounded away from 0, so it's finite and well away from 0, then when I take the logs of these, I'm just going to get finite numbers. This is bounded. We're going again to show that this one goes to infinity, and that means this sum goes to infinity, and that will show us there are infinitely many primes congruent to 1 mod 8. Similarly for this one here, we show that diverges. These are all finite, this is finite, so this diverges, and that gives me infinitely many primes congruent to 3 mod 8. So let's have a look at L of S and chi1 firstly. Well, that just looks like this. This is just going to give me, again, exactly as we saw before, it turns out to be this sum, and that diverges to infinity as s goes to 1. We need to show that the other L functions are bounded and away from 0 as s goes to 1, and I'll show that in a second, and it will then follow that there are infinitely many primes congruent to 1 mod 8, 3 mod 8, 5 mod 8, and 7 mod 8. So it remains simply now to convince you that these other L functions are all bounded and away from 0. So we'll do that here. It's fairly easy to show for L of S and chi2. It's not very difficult to show that L, this is between 2/3 and 1, so it's bounded away from 0. I'll leave that as an exercise. For L of S and chi3, then this is just, but in fact the proof of this is very similar to what I did in the earlier section, so you can have a look at that and see how to get this result. For this one, so here we write out what the sum is. It's 1 plus 1 on 3 to the s minus minus plus plus. So the signs are not alternating. They're going in a slightly, well, in a regular pattern, but not alternating. Now I just observe that for n equals 2, 3, and 4, and so on, this sum here, I'm just mimicking 4 of these terms here. So I'm just taking 4 of these terms, and I'm going to rearrange them slightly. So once again, all of these infinite series for s bigger than 1, these converge absolutely, so rearranging the order is okay. So I'm going to take this one minus this one, and then plus this one minus that one. And the point is then that each of these is going to be, so this sum is going to be positive for s bigger than 1. So I'll leave you to check that makes sense there, that when I do that, this sum is bigger than 1. Now, that means L of S and chi3, so if each one of these things is positive, then I can just take the first 4 terms. I can say L of S and chi3 is bigger than just the sum of the first 4 terms. And once again, I can say this is bigger than, I can toss that term away and just take these ones. And then I can say this is bigger than, I can toss the S away. And if you simplify that, you get 23 on 35. Well, just to make the numbers a bit nicer, I'm going to say that's bigger than 23 on 35. And that enables me to divide by 5, so it's 4 on 7. So that says L of S and chi3 is bigger than 4/7. And so that means it's bounded away from 0. I need to show that the L of S and chi3 is finite. So again, we come back to the series here. So plus dot dot dot. And I'm going to bracket these together in pairs. So I've got 1, 3, 5, 7, 11, 9, 11, and so on. And I can write that then, this now is an alternating series. So I can write it as minus 1 to the n a sub n, where the a sub n's look like this. So I'm just mimicking the terms inside here. So this is an alternating series, and the general term for s bigger than 1, bigger or equal to 1, these terms are going to 0. So this is an alternating series. For s bigger or equal to 1, the an's are all going to 0. And you can check easily that an plus 1 is less than an. And so this sequence is a monotonic decreasing sequence. And so by Leibniz's test, the series converges at least conditionally by Leibniz's test. That's all we need at the moment. And that means L of S and chi3 converges for all s bigger or equal to 1. And that means it's finite. And so I can take the logarithm of this and I'll get a finite number. Now you can do a similar argument for chi4, for L of S and chi4, which I leave you to do. And that shows that all of the L functions are bounded away from 0 as s goes to 1 from above. Now, I'll just outline what we're going to do for the general proof, and we're going to need some technical results and some complex analysis results before we actually do the full proof, but let me just give an outline of the proof. The general result, which is known as Dirichlet's theorem, which states that there are infinitely many primes congruent to B mod A whenever A and B are relatively prime, i.e. that's the set B plus Ka, so B plus A, B plus 2A, and so on. This is an arithmetic series, and provided the first 2 terms have no common factor, then that arithmetic series will have infinitely many primes. So that's Dirichlet's theorem. And now the key steps in proving the result are to show that, 1, we have to show that L of S and chi is bounded away from 0 as s goes to 1 for each non-principal character chi, which is what we've been doing in the examples up till now. So we're going to do this by showing that the series L of S and chi converges for real part of s bigger than 0. That's not too hard. And more difficult, we want to show that L of 1 and chi is not 0. Dirichlet didn't really do this to what would be modern rigorous standards, but we will do this, and that's the more difficult one, to show that L of 1 and chi is not 0. We then need to show that L of S and chi 1 diverges as s goes to 1. from above. We're going to do this by extending the zeta function to an analytic function valid for real part of s bigger than 0, with a simple pole at s equals 1, and we're going to relate this relate L of s and chi1 to this new function. The third step then is we going to, for each b, we need to pick out the primes that are b mod a and take this sum of 1 over p to the s. So where p is a prime congruent to b mod a, and for each b we want to write this sum as a linear combination of the logs of the L functions, as we did in the other earlier examples, and this is going to be done using the orthogonality properties of characters. Then as s goes to 1, it's going to follow that this sum then diverges, and so there are infinitely many primes in this particular arithmetic progression. Now again, we're modelling all of this on what we did with Euler's proof that sigma 1 over p diverges. And now in the previous examples, the characters we played with were real valued. In general, this of course is not going to be true, and so we need now to be concentrating and thinking of s as a complex variable. Therefore, we're going to need some results, just to remind you of some important results to do with complex function theory, and we'll be doing that in the next section. Some of you might be happy that you've seen a couple of examples of how Dirichlet works and decide that's as much as you want, but for those interested in seeing the actual full proof and the technical details, then you can watch the remaining videos of this chapter.